8. So that's, I added them. Now I multiply it by G. 6.673 times 10 to the power negative 11. I get 4486666 after a lot of sixes. Then I multiply that by 2 and then square root it. I get a pretty big answer here too. That's equal to 943.3 kilometers per second. So yeah, I got 943.256 point something. So I go to the left 3 spaces. So 943.3 kilometers per second. So it is even faster than the speeds that they would have. Okay? Well, that's not necessarily because the comet's mass was less. Because I probably know you're thinking, well, the comet was lighter. No, remember the mass of the comet canceled out. It didn't depend on the mass of the comet. It could be another planet, you know. But what mattered is that the comet, remember, like that, the comet was able to get pretty close to this guy, so it has a very low potential energy, and it has a potential energy with this guy. So basically, you're adding 2 negative potential energies. So the comet has a potential, it's bounded to this planet, it's bounded to that planet, it has negative potential energy for both of them, which adds up. Whereas when they collide with each other, they have a potential energy with each other only. So there's only one negative potential energy. And plus, they are bigger objects, so that their centers are farther away from each other when they hit each other, you know? So it's really not the fact that the comet was light. Okay, how about, let's do the last one, the escape velocity. Okay? C. This is kind of like the comet problem in reverse order. What's happening here is you have to give the rocket a certain kinetic energy so that it comes out of the potential well that it is in. Okay, whenever you look at astronomical tables, they tell you the escape velocity of different planets. For example, the Earth's escape velocity is 11.2 kilometers per second. The escape Earth is 11.2 kilometers per second. And then escape velocity from, let's say, Jupiter is 60.2 kilometers per second. So what's happening here? Well, the heavier it is, the harder to escape from that potential well, right? So basically, whenever you are on the surface of the planet, you have a potential energy of negative gm over r. So basically, the idea of escape velocity is negative gm over r is your initial potential energy. Okay? Plus your initial kinetic energy must be equal to 0. So you must give it a certain kinetic energy to give it a kick, so that you will be able to go out to infinity. So you have half big M little m plus half little m v squared is 0. M cancel, just like the mass of the comet cancel. So the escape velocity is 2, it's going to equal 2gm over r square root. So that's the equation of escape velocity for a single planet, or for a single star. It's proportional to the mass of the planet divided by its radius. So if it's a heavy planet, it's going to be hard for you to escape from it. Okay? If it's a big planet, it's going to be easy for you to escape, because if it's a big planet, you're farther away from its center. It's easier for you to escape. If you double the mass, double the radius, no effect. Okay, no effect on the, you double the mass, double the radius, no effect on the escape velocity. Triple the mass, triple the radius, no effect. Okay. Okay, how about now, what would your escape velocity be for the for the two stars? So basically we have to say, he's got potential energy with both of them, right? Just like the comet had potential energy with both of these stars. So I'm going to say negative g mass of the second star times the mass of the rocket divided by the radius of the second star. Then he's got potential energy with this guy, negative g mass of this star, over the distance is what? Well, the distance would be from here to here was 40 times 10 to the 8th. And then remember, this one was 9 times 10 to the 8th. So it's going to be 49, right? So let's call that one what? D plus R1. The radius of this guy plus the D. Or sorry, actually, no. What matters is that it's the distance from the center of this to the center of that, which is D, plus the radius of that guy, right? So the radius of this star doesn't matter if you're trying to escape from that star. Okay? If you're on this star, then the radius of that guy wouldn't matter. Okay? And then you have little m. And then plus the kinetic energy that you're going to have to give it is going to equal to 0. U initial plus K initial is 0. Okay, so then the little m cancels again, and you have basically half b squared is equal to, again, this thing, 6.673 times 10 to the negative 11. And I'm going to factor that out, and then the mass of this star is going to be 6 times 10 to the 30th divided by the radius of this star, which was what? 9 times 10 to the 8th, plus the mass of that star over the distance between them, right? So 40 times 10 to the 8th plus 9 times 10 to the 8th, so 49. Let's see what that is gonna be. So we have 6 divided by 9. I'm just doing this part now. 6 divided by 9 plus 2 divided by 49. Then times 10 to the, what is this here? Times 10 to the, this is 22, right? Times 10 to the power 22 equals, times this thing, times 6.673 times 10 to the power negative 11. Okay? Then you gotta remember to double it, then square root it. 971.7. So escape velocity, 971.7 kilometers per second. So that's a lot harder to escape than Jupiter. And is that the faster velocity than when the comet was at that point? It should be, right? Because you are now closer to even this planet. You have a bigger potential well. I'm pretty sure that other one was 900 something, right? Even lower than this. So it should be a faster escape velocity. So you need at least 971.7 kilometers per second to escape out to infinity and escape from the gravitational field. Okay, so next week we're gonna then concentrate on satellite motion as the planet goes around the star, what is its period, and we're gonna prove Kepler's law, and we're gonna talk about other regular satellites. We're gonna find the height required for a satellite to have geosynchronous orbit, and we'll talk about the energy of a satellite as it's going around and how we could possibly tap into that energy, and then we'll end with that chapter 13 will end. Okay, bye-bye.